Oh yeah, horizontal directional drilling. Check this baby out, man. This is the beast. This is for your larger diameter, like sewer pipes and things like that. But then we have some smaller directional drilling. You see the guys out running gas lines and stuff underneath the driveways and out along the roads and stuff. It can be used for installation on geothermal also.
Charrington introduces the next generation of HDB. Horizontal directional boring. HDB. The need for longer and larger diameter crossings while meeting the intense scrutiny and compliance of new environmental regulations has provoked Charrington to revisit one of its earlier developments for installing large diameter pipelines. Technology originally developed by Charrington in 1978 and subsequently shelved after our invention of a more cost-effective method referred to as pre-ream and pullback. Meeting the needs for larger and more environmentally sensitive projects, HDB is again being applied as means of installing directional drilled pipelines. HDB significantly increases the limits of directionally installed pipelines, benefiting both land and shore approach crossings. The principles of the HDB process involves attaching a drilling module to the leading end of a non-rotating product pipe or casing. The module having the means of rotating the cutting bit, a pressure-sealed articulating joint allowing the leading end of the module to be redirected during the course of drilling, providing directional control along a predetermined course. Also contained within the drilling module are internal pumps designed to pick up bentonite slurry and cuttings directly behind the advancing bit, transporting the cuttings back to the surface for process and recirculation. This essential process ensures that solids are picked up and transported out of the borehole, preventing solids from collecting within the annular space around the pipeline. As the drilling fluid is pumped through the drill head, the annular pressure increases slightly until the suction pump is started. Once the suction pump is started, the annular pressure returns to approximately the static pressure. The bentonite supply pump and the suction pump are synchronized at the surface by monitoring the annular pressure with the sensors within the drilling module. Controlling and balancing the static pressure ensures that pressure does not build within the annular space.
Oh, did we lose it? It's up there, guys. Hold on a sec. Hope we're not losing our internet. No. Yeah, here we go. We got it. And check out the sweep here. This is important.
The HDB method utilizes a pipe thrusting clamp anchored in a subsurface pit, or alternatively a ground surface location to slowly advance the product pipe and drilling module forward as the formation is penetrated. After the pipe assembly is thrust forward, the clamp is pulled back to accommodate a new pipe segment. The new pipe segment is lowered into the launch pit and welded into the previous pipe segment. The clamp is then secured to the new pipe section, and the drilling assembly is advanced once again. Locations that will accommodate pre-welding the pipe string in segments or in its entirety can be placed on rollers and threaded through the clamp assembly, allowing a continuous feed of the pipe string. The ability to understand the future is based on one's profound understanding of the past. Cherrington has been a name synonymous in pioneering and development of horizontal directional drilling technology for over 40 years. As a result of this ongoing commitment, Cherrington has developed not only the foundation, but the method and standards practiced by contractors worldwide in performing HDD services. For more information on horizontal directional boring or Cherrington's pipe thrusting equipment, contact Cherrington today.
Nice, huh? So we're going to take a look at some smaller applications here. An application you can use in your backyard for routing geothermal ground loops. So you notice they mentioned the annular space, or the slightly oversized drill head allows then the pipe to slide into the sleeve, so they need to have a little bit of room in there, some wiggle room. So in drilling part 8, we're going to look at cementing, or dealing with that grouting, as they called it.
Cementing is the process of mixing and displacing a cement slurry down the casing and up into the annular space behind the pipe. Once in place, the cementing is allowed to set, bonding the pipe to the formation. Oil field cement is made up of various compounds of calcium, oxygen, silicon, iron, and aluminum. The relative amounts of these compounds in the cement, as well as the fineness to which the material is ground, will determine its strength after setting, the rate at which its strength increases over time, its resistance to sulfates, and its setting time. The API has classified cements according to these properties, and choosing the proper class of cement for a given section of casing will depend upon the depth, and therefore the temperature at which setting will occur, the time allotted to mix and pump the slurry, and the strength required to withstand formation pressures and support the casing. Various chemical accelerators or retarders can be added to the slurry to speed up or slow down the setting time. Increasing temperatures reduce the time necessary for cement to set, so deep wells can become difficult as required pumping time increases while thickening time decreases. Retarders will usually be required to prevent premature setting of cement inside the casing. Other additives to cement include those also used for drilling fluids and are added for the same reasons. Bentonite for density reduction to avoid formation breakdown. Hematite or barite for density increase to offset high formation pressures. Lost circulation materials to prevent loss of cement into voids, and friction reducers. Friction reducers are added to permit the cement slurry to enter a state of turbulent flow at lower pumping rates and therefore at lower pumping pressures. This reduces equipment wear and horsepower requirements, as well as avoiding formation breakdown pressures. Turbulent flow is important to help promote complete mud displacement ahead of the cement, preventing the channeling of mud, which can lead to behind-pipe pressure communication.
Such mud channeling is the predominant cause of cementing failure, and much of a good cementing procedure is focused on preventing this from occurring.
Several techniques which are often combined are pipe centralization to allow uniform displacement of the mud by the cement, pipe movement, either reciprocation or rotation with scratchers to improve displacement in enlarged hole areas, and the high displacement rates and turbulent flow regime mentioned earlier. A good cementing procedure will also provide the following directions. First, condition the hole by reaming out tight spots. Condition the mud to remove cuttings and maintain a low viscosity. Install a guide shoe and float collar to prevent over-displacement. Where appropriate, install scratchers to remove mud cake from permeable zones and install centralizers at appropriate intervals. Use a cement slurry as heavy or heavier than the drilling fluid to keep cement in place in the annulus. Be certain to select the correct classification of cement depending on hole conditions and strength requirements. Calculate slurry volumes using a caliper log and increase by an appropriate safety factor to avoid under-cementing. Pump plugs before and after the cement to ensure proper displacement. Maintain tension in the string while the cement sets. And remember to pressure test the cement job prior to drilling out or perforating.
Another aspect, drilling, cementing. The mud guy, the mudder, not your mudder, not your fodder.
An important difference between drill pipe and drill column.
But the mudder's a very important person in the large-scale drilling well, and
Cementing is the process of mixing and displacing a cement slurry.
in small-scale drilling also. Here's the Halliburton cementing schedule. Lightweight cement, or Thermalite as it's called. A resource that you can take a look at here. It's in the central column of your course. We take a look here at Thermalock. This is cool stuff. I'd like to see how a guy could incorporate this into a building process. Thermalock cement, solid investment. 2007 marks the 60th anniversary of Brookhaven National Laboratory. Brookhaven. The whole idea is that they developed a Thermalock cement, and it's based on a air injection process. It's take a look at that on your own there. But it lightens the concrete, makes it more pliable or able to withstand higher temperatures. Its functional temperatures ranging from 140 to 700 degrees Fahrenheit. And the chemical makeup is important too. It also depends on the surrounding strata, the surrounding materials that you have. So something you probably didn't realize is how important the cementing aspect is, or how important the mudders are. So check out the journal here and this, shall we say, library or catalog. Brief history on the art or the science of cementing. So you've got to get the pipe in contact to conduct heat well.